Hello, I'm Lin Luo from the SketchX Lab, CVSSP at the University of Surrey. I'm going to present our work, Structure a Well 3D VR Sketch to 3D Shape Retriever. Let's assume we have a large collection of 3D shapes. In this example, we have a collection of 3D chairs. The user has some idea of a shape that they are looking for. In this work, we address the problem of retrieving an envisioned shape from an existing gallery of 3D shapes. First, to solve this problem, we need to choose a suitable query modality. The common query options are text, 2D sketch, and in our recent work, we proposed a quick 3D VR sketch as a new query modality. Although text is the most commonly used query type, it is hard to convey spatial structure through text. In this example, the user has some shape in mind that she or he wants to retrieve. Even with a fairly detailed textual description, the returned results are still likely to not match the imagined shape. Such system would leave the user unhappy and frustrated. 2D sketch was shown to be a more suitable query for 2D images retrieval. However, multiple 3D shapes can project to the same 2D sketch, making it less suitable for 3D shape retrieval. In our previous work, we proposed a new query format, a quick 3D VR sketch, created while wearing a 3D headset. Here we show some examples of collected sketches. We showed that promising results can be achieved. Thus, in this case, the queries are 3D VR sketches of envisioned 3D shapes. And here are the top 5 retrieval results. You can see that the ground truth is frequently returned among the top 5 retrieval results, highlighted with a green square. Let's have a closer look at the retrieved shapes. We observed that many irrelevant shapes are returned among the top retrieval results obtained with the previous work, such as the bench in the third example. With this work, we address how to improve the relevance of the retrieved shapes. In our paper, we also propose new evaluation criteria to account for the relevance of the top retrieval results. Now it comes to the specific method we propose. In our previous work, we used contrastive learning with a triplet loss, typical for fine-grained retrieval. Triplet loss operates on triplets. First, an anchor, which is the 3D sketch in our case. Then, a matching example from a different domain, referred to as a positive. In our case, it is a ground truth 3D shape. And any other example from a domain different to the anchor, referred to as a negative sample. For each input, we obtain its latent representation and pass to a triplet loss. Triplet loss ensures that, in the latent space, the distance between an anchor and the positive is smaller than the distance between an anchor and any negative samples, and the distance differences should be larger than a predefined constant margin value m. We propose an adaptive margin scheme so that different negatives have different margin values. In our work, the margin value is driven by 3D shapes similarity. Assuming that we have a positive 3D shape example, and we can establish a ranking of how similar the other 3D shapes are to the positive. Then, we propose a mapping strategy between the 3D shape similarity and the margin values. Please refer to our paper for the details. To compute shape similarity, we rely on the fitting gap that computes the distance between two 3D shapes after deformation. In the bottom, you can see deformed shapes and their predicted similarity to the shape on the left. Compared with our previous work, the adaptive margin helps retrieve shapes with higher structural relevance. In summary, our work addresses the problem of 3D shape retrieval from a sparse 3D VR sketch. In particular, we study how to improve the relevance of top retrieval results. We propose an adaptive margin selection scheme driven by 3D shape similarity. And we study how well shape similarity can be addressed with the fitting gap. For more details, please refer to our paper and project page.